Well, welcome to Depop. First of all, I'm going to keep the introduction about the company short and take the opportunity to give a little bit of context to why we built the system that John will present later. But for those of you who haven't heard of Depop, we're a marketplace. It was founded in Italy, in Milan, roughly 7 years ago. And I think the original target was to have 100,000 users. It turned out the idea was quite a bit more popular and successful than that. So within a few years, we grew to 30 million users today, 3 million of which are active every month. We're in the UK, in the US, Canada, Australia, and of course also still Italy. And we're seeing roughly like 50% growth year on year when it comes to how much we sell, which is currently roughly 30,000 items a day. And we get 100,000 new items every day, so we obviously try to sell more of those. And all of this rapid growth was quite a bit of a challenge for our backend infrastructure, I would say. And I'm going to show you some of these challenges before I hand over to John. Good. So in the beginning, our backend looked like most backends. There was one backend application, one database. It's quite easy to manage at this point. But then the rest of the business was also interested in this data. So we did what most companies do. We had a data warehouse, an ETL job. The data is synchronized into the data warehouse. It's okay again. Everyone can access it. But then as the company grew further, it became more and more complex to manage this one monolithic application. And this is when we made like a strategic investment into Scala, and we decided to move towards a service-oriented architecture and add new services which will be written in Scala, or which were written in Scala actually. So we kept adding more and more of these services. It was great in the beginning. Made it quite a bit easier to work with the backend. But then, unfortunately, they started talking to each other. And almost all of them started talking to the monolith. And each time there was a schema change in one of the APIs of the monolith, we had to change all other services, and redeploy all of them, which was, wasn't great. But then it went on. The business came again, wanted access to this data again. So we added more and more ETL jobs, synchronized all the data into our data warehouse again. And naturally, there was also dependencies on this warehouse. So there was dashboards and analytics services and data science applications. And at this point, essentially, what's here is a distributed monolith. If you change one thing, you have to deploy all of it. It works, but it makes it quite slow to change anything. So it's not great. So we moved towards this kind of architecture, especially on the data side of things, so on the right-hand side here, where we move towards event sourcing. So all the asynchronous events of our backend are exchanged via message broker. And then we have an ingest service that collects all these events and sends it onto our data lake. And with the data lake, usually what you try to do is like a schema on read. So when you write events to it, you don't care what it is. And at the end of the day, what you do is you say like all these applications that still depend on it, it's going to be their problem, which is good for the backend engineers. They can move quicker again, but it causes some issues that I'm going to show you right now. So as a business evolves, and Depop is no different, so does the data. So here's an example of an event of a sold product. When a product is sold, this kind of event is emitted. But then we went international, and all of a sudden it was important that we know which country it was sold in. So, it's quite easy. You just add a new field. Everything is still fine, but it already gives us a slightly uneasy, feeling because it might not always evolve that gracefully. Some of you might have noticed the price was a floating point number, which is not usually a good idea if you're dealing with currencies. So easy fix. Just change it to a string. Backend is happy. But on the analytics and data side of things, it might cause issues because if you now load all this data, you have inconsistent types. And for those of you who work with Spark know that often doesn't end very well. So we made quite a few people unhappy there. But the schema isn't the only thing that potentially changes or is causing problems. Like in this case, as an example, like the event time can be serialized like this with milliseconds in the timestamp. But since we now have a distributed backend, some other service, might be configured slightly differently, use a different stack, and emit events that are in a different format. And then again, if you want to parse this, you might run into issues. There's obviously solutions to it. One solution is to just have a parser for every single date format, but that's not really what you want. And at this point, we're like ready to flip the table and say, okay, hold on, we need to change something here. So essentially what we want is a consistency across all the data producers, which can be the apps, so the iOS and Android apps, the web, or also the backend services. And we also need some sort of a way to future-proof the data in our data lake. So in short, we want control of our data. The reason we did it right now is we're about to insource the user tracking, so the way we track how our users use the app. And this is like in one go going to add like a couple of 100 million events a day in like hundreds of different forms. And if we don't get it under control now, it won't really be usable. So we won't be able to make data-driven decisions. And we won't have a sane foundation for machine learning services. So I told John to build a system with the objectives of like data consistency, future-proofing the data, and gaining back control. And he's going to walk you through how he did it.
Okay, so we decided to make a schema repository. This is a library that's going to be used across all of our services, and it needs to do the following things. These schemas need to be able to generate classes in other languages. We need to be able to serialize them in and out of some format, and when the business change, we need to be able to do schema migrations. And the final thing is field validation, which is we don't want that date format to come in at any point. So we need control of our data. Cool. So firstly, we'll tackle consistency. As Robert addressed, when you're dealing with Spark and Parquet, these things are optimized for different types. We might get an error that looks a bit like this. So imagine you have a integer field and a double goes in there, and we try and read out the event. We're going to get an error like this because it doesn't know how to process it. That means we can't read any of the data that comes from that partition, which is going to mess up all of our downstream systems. So to ensure the safety for sending our events through the data lake, we thought, well, APIs share a contract between services, so why can't schemas? So we started looking at schemas. So we looked at a few different types. The first one that we looked at was protobuf, which didn't solve all of our cases. Then we looked at Avro, and we came up with this strategy. So what we're going to do is we're going to define some case classes in Scala. This is good because most of our services are written in Scala. So they can download these from the library directly and use them. We can put extra functionality on these classes that they can use, which we will see later. From these case classes, we're going to generate schemas. And then from these schemas, we can generate classes for other languages, for the producers, say in Python or Swift or something. So we can have consistency across our producers. Let's have a look at this class in the bottom. It's quite important for us. So it's about a user session. So these are all the things that happen in a particular session for a user. So we have some meta information at the top, which we're not really interested in today. But at the bottom, we have events, which is a list of this type called all events. But our all events are different things. So we might have a like, we might load a new view, we might have a search result. And they're not necessarily related in any way. So we can't really use inheritance to define this type, all events. So how did we do it? Well, we're going to use a co-product from Shapeless. Co-product is a way of defining an optional or union type. Some of you might have seen it. And it uses this list structure in order to create it. For those who are familiar with Shapeless, you might have seen the H list, which is a way of encoding a list of different types. So here we have a list that has an integer, a string, and a Boolean, and it's all type safe and we're all happy. A co-product is kind of similar. It's constructed in this list-like way. If you see at the bottom here, we have 3 values that all have the same type signature. A co-product will say we're going to have exactly one of these types that are in this list structure. So the first one we've got an int, the second we've got a string, and the third we've got a Boolean. So we're going to use this in a minute. So this slide is a bit pretentious to call it set theory, and no, this isn't the slide. Suppose we have a carrot, and then by the properties of union, we also have a banana or a carrot. And in general, for all, if you have A is true, then for all B, A union B is true. We're going to use this property later, so remember it. This notion of co-product or union types allows us to create a list of all the events that we're interested in seeing. So we define this type to be all events equals product like action, union, search result, union, new view, etc., etc. And then we can use this because Avro has support for serializing these union types into their schemas. So how did we create these schemas? Well, I have the code at the end of the talk, so if anyone's interested, but we're not going to go through it right now. We've got more important things to do. But we made an SBT task that when our schema library is compiled, it iterates over all the classes that we're interested in putting in this all events, all session objects, and it creates a schema here. This is the one for the like action. We would show the one for the session, but it's so big it wouldn't fit on the screen, so it wouldn't be any use to anybody. So we've made all these classes. We've made the schemas, and we can translate these schemas through known libraries into classes of different types. But we need a way of sending them between services. We're not using the Avro binary format because most of our services already communicate via JSON. So we need a way to serialize and deserialize these events in and out of JSON. But they've got this nasty co-product at the bottom, which isn't easy to do. And this co-product is arbitrary. It contains a number of events, and we're not going to constrain ourselves on that. So we put this. We tried using this library by Julian RF, and it's quite good. You can serialize most case classes in one line, but if it contains a co-product, it doesn't work. So put this Stack Exchange question on, and then our dear friend Travis Brown replied because he loves functional programming, and came up with Circe shapes. So we came up with this implementation of JSON serialization for generic case classes. So how it works is we have a class A and a representation which is a subtype of a H list. And given we have these implicits, the first one is a gen awks, which says, given I have a case class, can I turn it into a H list representation? And the second implicit is saying, have I got an encoder for that H list? If I provide these two, then I can contramap the encoder of the representation back into the encoder of A. And in doing so, we do a similar thing with the decoder. We can deserialize and serialize any case class in just with these implicits, which is cool. So we solved the first problem, which was consistency using these schemas. The next thing we want to tackle is future-proofing. So we need to be able to do schema migrations when the shape of our events change. So what we did is all of these events would extend this trait called version schema. That enforces your your event to provide an upgrade path to the newer version of this particular event type. We're going to use this trait at the bottom called latest version to bound this evolution. And then when we receive an event, we're going to call upgrade to latest, which is going to iterate over these types until it reaches the latest version, and then it will just return itself. So in one line, we can seamlessly upgrade to the latest version of any event, which is also cool. So that's future-proofing. Control, this is the interesting part. So I'm going to apologize in advance for this slide. You might find it funny. I'm not sure if I love it or hate it or not, but we're going to give it a go. So we want to do some field validation. So let's do it together. What do we think about this? Do you think this is field? Hands up for who thinks this is a field. An alarmingly few amount of people think this is a field. Okay, but it is. What about this? For the keen-eyed 3, and have you all seen this before? 3 keen-eyed people in the audience have noticed that this is a field. This is the field of rational numbers. Yeah. What about this chap? Who thinks this is a field? Well, no, this is a fielding. So that's a cross. But the point is that we want to validate our fields so we don't get our null fieldings into the data lake. I didn't think I'd say that today. So we're going to prevent ingestion of incorrect data. Sweet. So in order to do this, we've made this validation trait. We're going to use the cats validation non-empty chain in order to do our validation. So the way it works is we provide some logic to say whether a class is valid or not, or an instance of a class is valid or not. If it is, then we'll say it's valid. If it's not, then we'll say it's invalid. And the non-empty chain will collect all of these validation errors and then provide them in one list to the client should we want to surface it. So we need a way to construct a validation for any arbitrary co-product because our session events could be any. We don't know which type, when we receive an event, it's going to be. So we need to be able to do it for anything. So we're going to use the list-like structure of the co-product in order to do this. Okay, so suppose we have an arbitrary co-product which is of type Z, which is made up of A union B union C, blah, 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 all the way up to C nil. C nil is the bounding type for a co-product. We're going to use induction to create a validation of this product. So the base case is, can we create a property of validation C nil? If we can, that's good. And the inductive step is, suppose I have a validation for the head of this list-like structure and a validation for the tail of this list-like structure. Can we create a validation for the head union the tail? If we can, then we have a validation for Z, given that we have a validation for all of these subcomponents of the type. Does that make sense? Sweet. Right, let's do it. So suppose we have an instance of this Z, and we want to find an implicit validation type for it. The base case is C nil. For anyone who knows co-products, you can't create an instance of C nil. So suppose we did, we'll just say it's valid. Good. So it looks like this. The inductive step. So suppose we have an implicit validation for the tail of the co-product and the head of the co-product, and we have an instance of Z which is either in the head or the tail, then we want to construct this new validation. So in doing so, we need to implement this method here. So let's do that. We're using the list-like structure again, and we're going to pattern match it on it as we would if it was a normal list. So with a normal list, we'd say, right, well, does it belong to the head or does it belong to the tail? Well, if it belongs to the head, then we're going to call the head validation method. If it belongs to the tail, we're going to call the tail validation method. And then we're going to match on the result of that. So if it's a valid head, then by the bananas carrots property, which is a term I've just coined, it's also a valid head or tail. The same goes for the tail. So if it's a valid tail, it's also a valid head or tail. If it's invalid, then we don't care. It's an invalid head or tail because it's invalid. We don't care. We'll just return the error. In order to do this sort of union lifting type operation that we're talking about, we need these implicits at the top, which basically say, I know that my element belongs to the tail, or I know that my element belongs to the head of this new union that we've created. So altogether, we have this construct, and the result is, if we provide a validation for each component of our co-product, we inductively create a validation for the whole thing. Cool. So this is how we use it in the wild. We've made a separation here between the session meta information and the events themselves. This is because if we get an invalid event in a session, we can drop it. We don't really want to lose the rest of the information. But if the session meta information is wrong, it doesn't really make sense to keep the rest of the event. So we can make a business decision here to drop it. We iterate over all of the events that happen, validate each ones, and if there are errors, then we use the combine method of the non-empty chain to aggregate them all together and surface them to the user. So we get an error raised like this that says we've got validation errors. The event type bananas was not equal to the event type of product like action, or event type carrots wasn't expected search result view. Cool. So now we've achieved all of our goals. We've got consistency through the schemas. We've future-proofed via schema evolution. And we've got control of what comes into the data lake on a field level with the field validation. So, in conclusion, we want to keep all of our data as clean as possible. We're going to use schemas to do this and field validation to protect the content.